What's up guys, it's me Sir Ernest, and today we're going to discuss example 1.10.2 of Fowles and Cassiday 7th edition. Now suppose the position vector of a particle undergoing circular motion is now given by r equals I sine omega t I hat plus b cosine omega t j hat, where omega is a constant. So from here, we can talk about a lot of things. Now, here, it's mentioned that this should be moving, or this represents an object undergoing circular motion. Now, let's check by calculating the distance of the particle from the origin. Okay, so for example, if this is your x and y coordinate system, and let's say the particle is here, this will be the position. Okay, so the distance of the particle from the origin will just be the magnitude of this position vector. So that's r. Sometimes we write this as absolute value of r vector, or just simply r. So when you see r without a vector sign, that means we are talking about a scalar quantity, in this case the magnitude of the position vector. Okay, so what we're going to do is just take the magnitude of this. So from here we can see that this would be the x and y component of your position vector in two dimensions. So we just take the sum of the squares, and then you take the square root. So this will now be equal to b squared sine squared omega t plus b squared cosine squared omega t. And then you take the square root. So here we can factor out b squared, and then we're left with sine squared omega t plus cosine squared omega t, which is equal to 1. Okay, and then that becomes b squared to the 1/2, or simply b. So you will notice that, remember that b here is a coefficient, so these are constants. So that means the distance of the particle from the origin given by this position vector will be constant, and that is particular to the circular motion. So that means the particle is always equidistant throughout the motion to the origin, which will follow a circular orbit. Okay, so that's it. Next, let's look at the velocity. Okay, so velocity of the particle. So the velocity is a vector quantity, and that is equal to the derivative of the position with respect to time. So here we just differentiate this function. So the derivative of the position function would now be equal to b omega cosine omega t I hat plus negative b omega sine omega t j hat. In this case, we can now define the x and y components of the velocity. So this is now your velocity vector. Very simple, right? Simple differentiation. Now, the speed, on the other hand, which is the magnitude of the velocity, will just be equal to the square of this. So that's b squared omega squared cosine omega t plus the square of this. So that's b squared omega squared sine squared omega t, and then you raise it with 1/2. So from here, again, similar to this, cos b squared omega squared can be factored out, leaving with cosine squared omega t plus sine squared omega t. So that's equal to 1. So that's b squared omega squared to the 1/2. So this will now be equal to b omega, which is again a constant. That means the particle, if the particle moves in this direction, the particle moves with a velocity that is always tangent to the position, to the particle, and it is moving with a constant magnitude. Okay, or moving with a constant speed. So so the motion of the particle under this equation, under this position function, is uniform. Now, how about the acceleration? Okay, so again we do another derivative. So this time we differentiate the velocity function. So here we now have the differentiating this function. We now have negative b omega squared sine omega t I hat plus minus, sorry, or plus negative, or just simply minus b omega squared cosine omega t j hat. So again, similarly, this will be your ax, and this will be your y component of your acceleration. Now you will notice that we can factor out negative b omega squared with we can factor out omega squared, negative omega squared. So that means inside this term we now have b sine omega t I hat plus b cosine omega t j hat. And what is this? Yes, correct. This is your position function. So in other words, the acceleration is just equal to negative omega r. So from our previous discussion about vector identities, or fundamental definitions, or multiplication of vectors with scalars, so you will notice that in this case, the direction of your acceleration is always opposite the direction of your position function. In this case, the acceleration will always point opposite the direction of your position. In other words, again, acceleration is always inward or toward the center. It's always pointing toward the center. So that's why we call this acceleration your centripetal acceleration. Okay, so when you say centripetal acceleration, centripetal literally means center seeking, because the acceleration always points towards the center. So if we're going to check the magnitude of the acceleration, we now have a equals b to the 4th omega to the 4th sine squared omega t plus b to the 4th, b squared. It should be b squared. So this is b squared omega to the 4th cosine omega t to the 1/2. So this becomes b squared omega to the 4th to the 1/2. So this will now be b omega squared. Again, a constant in magnitude. Okay, so the particle's acceleration is always opposite the position function r. That means it is always directed towards the center and has a constant magnitude. Okay, and finally, if we want to take the dot product between acceleration and vector, we can take the dot product of this with this. So taking the dot product, we now have negative cosine times sine. So this is negative b squared omega cube. So multiply this with this, sine omega t cosine omega t, minus minus, so that's plus b squared omega cube sine omega t cosine omega t, which is equal to 0. So this verifies that if the dot product of A and V is 0, so that means A must be perpendicular to V, which is what is we assumed or we set earlier. Okay, so that's it. That's your circular motion. That's example 1.10.2 of Fowles and Cassiday 7th edition. Okay, I hope you learned something today, and I'll see you guys in the next video. Bye bye.